All right. So I want to first apologize for the difficulties in pretty much everything that's going on with the coronavirus outbreak. And I hope that everyone is staying healthy and that you can bear with me as we work forward throughout the semester. So today we're going to start by using some of our quantum mechanical principles to talk about atomic spectra. So atomic spectra are really important because we can use them to evaluate all of the structure of our atomic systems that we were talking about for almost a month. And they're one of the best ways of looking inside of an atom. But one of the most important considerations that we have to take into account when we're looking at atomic spectra is the fact that we are using photons or light in order to look at an atom, or specifically the electrons around them. And it turns out that a photon has a spin. In fact, it's a boson with a spin of 1. So, just like we've been talking about so far, with the fact that I bring in a photon, it excites an electron, I have to obey the conservation of energy. Well, it turns out that if a photon has a spin, that means it also has an angular momentum. And it turns out this, so does an electron, both in terms of the orbital angular momentum and the actual angular momentum of the electron itself. But just like we have a conservation of energy, we also have to have a conservation of angular momentum. So our total angular momentum can't change. So I have uh, an angular momentum of 1 associated with the spin of the photon, and an angular momentum involved with the orbital component, and the angular momentum of the electron itself can't really change. This means that when these two combine, my electron will likely get excited to a different state, and its orbital angular momentum has to be either the orbital angular momentum I started with, plus 1, because the photon added to that speed, or if they essentially hit counter to each other, so photon comes in here, cancels out some of the angular momentum of the electron, it can also be the original L value minus 1. So let's look at this a little bit more pictorially. So I can imagine this as a photon coming in with an oscillating electric charge, interacting with, say, a p electron. So there's one of two possible ways that these two can combine. Either I can take my dipole moment, or essentially the bias in electron charge that comes with being a p orbital, and my photon can essentially cancel this out. So they end up adding together deconstructively. And what I end up with is an s orbital, because that dipole moment from the electron will cancel out with the dipole moment of the photon. And then I'm left with something that's, well, has no dipole. Or these two can add constructively. So the dipole moment coming in from the photon and the dipole of my electron, which it already has, can add together, and it turns out you can make it spin even faster, giving it a net orbital angular momentum of 2, generating a d orbital. You'll notice there's no way for this oscillating photon to combine with a p electron and generate a new p electron. Either my orbital angular momentum will increase or decrease. And again, one of the ways we can look at this is as a transition in the dipole moment. And now, being a physical chemistry class, guess what happens now? We prove it with the math. So we can look at the feasibility of an electron excitation by applying, of course, another operator. So the one we're looking at this time is the transition dipole moment operator. So we're going to label this guy mu hat, because we need more hats in the world. And so this is represented by negative, the electron charge. So essentially, how much charge do I have? And of course, the radial operator, how far out that charge is. the more charge I have further out, essentially, the more I've moved the angular momentum, which should make a certain degree of sense. Now, where this gets really cool is that it turns out that this dipole moment, transition dipole moment operator more or less stands in for the dipole that photon has coming in. So we can look at the excitation of light by looking at the integral of the wave function of my final state, which will have some dipole, the actual dipole of the light, and then the initial wave function I started with. So what I have is an orthonormal state of two wave functions. If these two don't overlap, so more or less if they aren't the same, it has an integral overall space of 0. Yay, orthonormal. But what can happen is that my photon can have a transition dipole moment that can change the wave function I started with. And if it makes it look like the wave function that I end with, then it might be possible. However, most of the time, this doesn't happen. And so if my initial and final wave function times my dipole moment operator gives me an integral of 0, it means that my light doesn't really allow me to go from state I to state F. And this is called a forbidden transition. And it turns out light can't do this type of transitions. So if you're trying to make that transition, good luck elsewhere, a photon won't do it. But, and here's the special thing, an excitation is going to be allowed if when I apply my dipole moment operator, it can turn my wave function, my initial wave function, to something that will overlap with the final wave function. Then that means it might be possible to go from state I to state F with a little help of a friend. But again, only if I have a non-zero integral, which gets a little bit tricky in orthonormal space. So not every wave function can make this jump. So we're going to need to figure out exactly what form of wave functions will allow this transition. But we already know it has something to do with the angular component. And my transition dipole is all radial. So what we can do is try and split my radial component and look individually at the transition of my dipole moment in the Cartesian coordinates, x, y, and z. And again, as has been going on for a while, and will continue to go on for a lot more, we're going to specifically look at the z coordinate, because we usually like to define this guy as the one coordinate we care about. We can choose any, but we like the z coordinate. So when we do this, we can express the transition dipole moment as the electron charge times the z coordinate, just like we did with the r earlier. But where this gets a little bit special is that I can expand z into being r times cosine theta. Because if I've got a cosine theta of 0 or pi, congratulations, I'm along the z. If I'm something else, this guy kind of goes to 0. So this is a good stand-in for the z coordinate. And where this gets really special is it turns out that cosine theta is related to one of our spherical harmonics. Most notably, L equals 1, m sub L equals 0. You probably remember this guy as the pz orbital. So nice little p orbital in the z direction. So, of course, we have to tag along our normalization constant because it likes to go everywhere too. So we can now use this expression for our transition dipole moment operator in the z direction. So if I want to actually figure out what my whether I can make the transition from I to F in the z direction, guess what? We have to apply our operator to a wave function. Go figure. And as is always fun in angular components, we have to do this over all space. This gets a little bit fun, but we can go ahead and start inputting all of our variables into each of these components. So, for example, we can take my final wave function and turn it into its radial and spherical harmonic components. Note that the radial components have no imaginary components, so I don't have to take the complex conjugate here. Spherical harmonics love to be complex, so we take the complex conjugate here. Input in my new expression for the transition dipole moment of the z component right on in, both in terms of the radial and the spherical harmonic components, and then again, my initial wave function, both the radial and the spherical harmonic component. But don't forget, when we're doing the integral over all space, this one gets a little bit messy. We have to put it in terms of r squared dr, sine theta d theta, and then of course d phi. Congratulations, we made a big old mess of an equation. So now we have to try and figure out a way to simplify this. So, good place to start is to separate it out into individual components. So we can pull out all my constants, and as has been a trick that served us well in the past, separate out the radial components, so everything that depends on r, versus the angular components, everything that depends on theta and phi. So when we do this, we have a nice little constant, a nice little integral over radius, and a nice ugly integral over the angular components. But at this point, it's really important to remember what we're trying to do. All we want to know is when my transition dipole is not zero. So when can I make a transition? Well, it turns out constants are never going to be zero, so we're good there. And then we have the radial components. Well, another way to think about this guy is that this is going to be more or less the average radii of the overlap in between these two expressions. Now, you can run the math to verify, but it turns out this guy is pretty much never zero as well. So, all of these terms can't be zero. Guess who can? It's our angular components. So let's take a little bit tighter look at my angular expression. So my transition is going to be allowed if this whole integral doesn't equal zero. So what is this really? It's going to be the combination of three different spherical harmonics. And it turns out this is actually a pretty well-known expression. It's a special case of the integral of any three spherical harmonics. One's going to be complex, the other two not. So it turns out that this has a nice special set of solutions. It's more or less when these two spherical harmonics added together will be the same as the product. So in mathematical terms, we say that this will be the case when m sub L, so this middle spherical harmonic, plus my initial angular momentum, plus the angular momentum of the added spherical harmonic equals the angular momentum of my final. Or alternatively, if the difference of these two is also equal to my final wave function. Now, this actually ends up being pretty nice because remember, we know one of our L values. So our L is just 1. So the difference in between my final and initial wave function has to more or less be plus or minus 1. That's going to be the only time that these three spherical harmonics are going to overlap. But we have another component as well. we've got the magnetic quantum number, m sub l, because m sub l will have to be equal to 0 plus my initial m sub l. Well, that's pretty easy. It means that for the transition in the z direction, my orbital angular momentum has to change by 1, either up, constructive interference with the photon, or down, destructive interference with the photon. But the direction won't change. So this is pretty cool. Unfortunately, it turns out that we dropped a couple terms. Specifically, we dropped the transition of the orbital angular momentum in the dipole moment in the x and in the y direction. So when you include the y and the x direction, it turns out not only does the orbital angular momentum have to change by 1, but it turns out I've got 3 possibilities for my m sub l value. It can stay the same. That's what happens if the transition's in the z direction, or if it's in the x and y direction, it can increase or decrease, but only by 1. So now what we've done is defined a small subset of wave functions that we are allowed to excite from and into. So we can apply this back to the hydrogen spectra. So we like to represent this visually using a Gaussian diagram, which is more or less this fancy way of drawing out the possible S subshells you can occupy, B and D, and what transitions are going to be possible between them. We'll use this a little bit more when we hit multi-electron systems. But it turns out if I start with a 1s electron, so ground state hydrogen, I'm only allowed to excite into the 2p, the 3p, the 4p, the 5p, the 6p, but only into the p subshell. You can never, using a single photon, excite into the s or the d. So what we've done here is we've seriously limited the states. It turns out with the m sub l rules that you can only go up or down one m sub l state, but since only -1, 0, or 1 are allowed for the p orbitals, this actually doesn't play a major role for this case. But where this gets really interesting is our classic Balmer peaks. So these are the ones that we can see with visible light. So let's say I took that 2p electron I just excited to, and I try and excite it again. Well, this time it can excite into the 3s or the 3d, but it can't excite into the 3p. But in contrast, if I have a 2s electron, it can excite into the 3s or 3p, 4p, 5p, any of the p orbitals. So a good way of kind of summarizing what can happen here is that an electronic transition, when driven by a photon, requires a change of the occupied subshell. Again, only by 1, so S can go to P can go to S or D, and D either goes to P or F. So we now have a much more restricted set of electron excitations that are possible. And it turns out this becomes really important and a lot messier when I start looking at multi-electron systems, because some of these subshells are already occupied, and it turns out these energies aren't the same for everybody. Say goodbye to the hydrogenic system. The other important thing to consider is that we've got to figure out how spin can play a role in these transitions and even into these various energy levels. So we'll be doing that next time. Take care, stay healthy. Let me know if you have any questions. Bye.